All right, well, it's 3 o'clock, so maybe in the interest of time, we'll keep things moving. Ed, are you okay with that? At Cisco?
Yep, we can go for it.
All right, well, there is one question in the chat that we haven't answered. And maybe, Darius, when you can speak to this, does NIST still collect all mass spectra using the S-Tune for Agilent instruments?
Yes.
Okay, perfect. Well, that's good to know.
No, that's not true. We do use the 7000, and it's by definition, since it's a 7000, has a slightly different tune, but the vast majority of them are on the standard GCMS instruments.
Okay, and the 7000 you refer to is a triple quad instrument.
Yeah, but we use it as a single quad.
Correct.
Well, if we have no questions, I will start the conversation. And also, I guess, do the panelists have questions for each other? James, you can't hear anyone? I guess I should type something in to ask.
I could work on it, Arun.
Okay, perfect. Actually, unfortunately, the first question I had was for James, but I guess it's it's a question for everyone. Because still can't hear anyone. All right, well, maybe the rest of you can answer. So James had said he likes to have all the mass spectral libraries that he can, access to everything, all the mass spectra. Is that how all of you feel? In terms of when you're trying to identify things, just as many options as possible?
Yeah. There's one huge problem that the Wiley library has an enormous number of partial spectra that can really throw you off. But except for that, I mean, there's a flavor and fragrance library that's quite useful, and there is the Swig drug library is useful. And so, yeah, I mean, if you've got more is better. But the very large number of partial spectra in the Wiley library, I don't think is very helpful.
Well, you can adjust the NIST search program to compensate for that. And the other thing is, in the latest edition, especially of the Wiley library, a lot of those partial spectra have been moved into what is called the legacy portion of the library. And the Wiley 12 main has better quality spectra in it. It still has a tremendous number of problems. But you can set the limits in NIST search to compensate for those partial spectra. And Jim has said that those partial spectra sometimes are very helpful to him.
Well, sometimes they are. I don't disagree with that. But there's so many cases where they're not that they're irritating.
Can you hear me now or not? No,
yes, we can hear you.
What you need to do is limit the search so it searches from 10 to 2000 so it doesn't do partial spectrum search. That helps. You can search, when I'm searching for model compounds and doing my NIST evaluation work, I search by Inchy key and then compare there and see if I find matches there. Sometimes you can do the reverse search to get the good results up. But I find it good for finding unusual ions sometimes that I don't understand in some of the new NIST spectra. So I do find it still very useful in my work. But I can understand what you're saying. It could be annoying. But if you set the limit so it says, I'm going to force you to look at the whole spectrum, then all of those ones that are aggravating just fall out and you never see them anyway.
Sure.
My opinion. Just my opinion.
Yeah. And I think that that's actually one of the interesting things about watching all four of you work through examples today was just seeing that there is a little bit of differences, but the end goal is the same, is to try and identify compounds, right? And actually, that was another thing I was hoping you can kind of expand upon, James, is your use of the spectralist databases. I know a lot of this session was about mass spectra, but you also use a lot of spectral-less databases.
Yeah, they work very well, amazingly well, especially for industrial type things. You can just find all kinds of things, and then I just interpret the EI fragmentation pattern or the MSMS fragmentation pattern to find out if it makes sense. And sometimes we'll order a standard. Sometimes it's just good enough that from the sample history, I know that they're looking for an antioxidant or they're looking for a UV stabilizer, and I have the diode array, and I can tell from the LCMS if it has the diode array spectrum of UV stabilizer or a colorant, or so there's a lot of other information. You don't often need standards. And then I go to the NMR and I look for it and see if they can. NMR is not very good if you just give them something and say, this is a mixture of 10 components. Tell me what it is. But you say, is this present? Well, that's much different. And they'll say, oh, yeah, that's present. I can see that. I don't know what this other stuff is, but what you're looking for is what you're looking for. Then they can quantitate for me. Then I can come back and I get it out of the mass spec lab. I send it up to the FID and the GC lab. I send it to the LC people, and they quantitate it, and it gets it away from me pretty quickly. So you don't have to have a standard to do things by NMR, and that's the power of. There's very few analytical techniques, maybe besides X-ray fluorescence, that you really do not need a primary standard to quantitate, and NMR is one of those.
Okay.
So yeah, the spectralist databases we use all the time. It's we reverse engineer other people's things by using their patents. If I know it was manufactured in a LCD extract and it was from Fuji, I just type in Fuji patent, accurate mass, and they'll have 150 examples, but mine will be the one that's there. They put enough there to confuse you, but with the accurate mass, there's no confusion whatsoever in the fragmentation data. That's what they're using in their LCD panels.
Sure. Yep. All right, so I have another question for Gary. And so you had mentioned, chromatography has gotten so much better, so you don't have to do as much subtraction, but sometimes, as you showed in your example, sometimes you still do. And dismisses it. I guess my question is, and you had used this word, and actually David had used this word, and maybe James had used this word as well, suspicious. You were suspicious of that resulting mass spectrum that you pulled out. I guess, where did that suspicion come from, other than experience?
Well, I don't know. I'm not sure. I mean, in some cases, it probably is experience. If you look at a spectrum and then you look at its neutral losses, and the neutral losses don't make sense, that's often that presumes that you can figure out what the molecular ion is. But if you're sort of saying, well, that looks like the molecular ion, and then I've got a big neutral loss that is 7, well, you know either that you've got the wrong molecular ion, which is often the case, or that you've got some sort of a mixture, or there's something else wrong. So that's one of the things that I look for. The other is, and particularly because I really only work with GCMS, if I have any retention information at all, and the compound that I'm coming up with just simply couldn't have come out then. It's too small a compound and it's being reported to be out at a very late time, or it's too big a compound and it's reported to be out very early, then that again is suspicious. It's not just the mass spec though. It's all the information you've got about the data usually.
Well,
we probably do about let's say we did 10,000 samples at Eastman a year. Probably on 2,000 of those we do chemical ionization mass spectrometry to confirm the molecular weight before we add it to the library. And if you can't do that, then forming a TMS derivative, like Dave said, is a poor man's chemical ionization. Sometimes you could just shoot a lot on your column, and you get enough neutrals in there that the neutrals will just give you self-chemical ionization, and all of a sudden your ion will start to show up bigger. That's not particularly good for your source, maybe, but it works.
Well, another thing you can do is you can increase your helium pressure going in there so that you get chemionization and get higher amounts of molecular ion present. there's another important thing too with regard to retention index. Although it's not infallible, the estimated index, like on one of these compounds that we identify with the hybrid search, does the estimated retention index for the proposed structure come close to matching the measured retention index? That's why it's so important to measure the retention indexes on compounds.
Yeah.
Yeah, I guess that's right. So we titled our talk Mass Spectral Interpretation, but really chromatography and mass spec are tied pretty closely. Is that right, Gary?
Yeah. Well, and particularly the AI data, the retention index calculated by RI are remarkably good. They're better than our old estimated method on a whole. There are certain classes of compounds that it's not very good for, but for the most part, it's a remarkably good tool. And I would say it is 90% of the time, if you don't have a real experimental data, then that AI retention index, which we have for everything in the database, is worth at least paying attention to. And whether or not it's going to solve your problems is another question entirely, but you definitely should pay attention to it.
Well, but we don't have a way yet of determining the AI retention index for an unknown structure.
Well, no one has a way of retaining anything for an unknown structure, but you mean for a proposed structure.
For my suspected structure.
Yeah. Well, we do, but it's not publicly available.
I think that's the key word there. Hopefully, with NIST2022, that'll be. Any comments on that?
You cut out there or something, Arun.
I was just saying, I think that the AI RI is not publicly available yet, but I think it will be.
No, it's released in the database, but the tool for calculating it for an unknown compound is not. It's something that takes a lot of computational power, and when you calculate one, you send it off to a server, and it takes 2 or 3 seconds. And if you're calculating a dozen or two, it may take half an hour. And so, not half an hour, but it's a very different way of approaching things, and it's done on a server at NIST, and it's not publicly available.
Actually, so then along those lines, do you know if the group contribution method is implemented as some type of software tool? If someone wanted to predict an RI for a
if you draw a compound and put it will the mass spec database will predict the group additivity version, but the group additivity version, it's sort of a function of the molecule you're dealing with. For a lot of molecules, it's actually quite good. But once you get more than a couple of nitrogens in the molecule, or you get more than one TMS in the molecule, it tends to break down, and we just haven't had time to readdress it and bring it up to date.
And if you have sulfur atoms, it doesn't work at all. There are no estimated. I think it's sulfur, but there's no estimated.
No, sulfur we've got. I'm pretty sure phosphorus we don't have.
Okay, maybe that's it.
I'm pretty sure sulfur works.
I guess another question I have, and now this is, I know, a really hard question to answer, but I love the phrasing "closing the loop" because it reminds me of my mathematical background of QED. Felt like, oh, this is how you feel good about something, where you've closed the loop on your analysis process. And so, do each of you want to speak on kind of what you need to feel confident when you're making a call? Maybe we'll start with you, Gary, since the closing the loop term came from you, and I was happy with that.
I don't know. I mean, it's a consistency, really, is what you're looking for. You're looking for nothing unusual in the mass spec, and you're also, if you have the retention data, and I think it's important to have the retention data, you're looking to see that it's also reasonable. I mean, I don't. I mean, some of this is just sometimes you have some information about a sample, and that helps enormously if you have some information about where a sample came from. But if you don't have any information about where a sample came from, or your information is so vague that it doesn't really help, then it's hard. It's hard to have that extra level of confidence that would come from. James was talking about the fact that he's got a certain industrial process, and this is something that came out of that industrial process. There's a reasonable sort of set of things that could happen in that, and so if this is unreasonable, if this is a process that didn't have any chlorine any place in it, and you're suddenly looking at what looks like chlorine isotopes, then you say, maybe I haven't really identified it, or maybe they told me wrong and there's something else going on. But it's sort of the sum of your knowledge. It's an organic process, and not. I don't know that I can give you a good answer to this question. I think I'll quit stumbling around.
Yeah, no, and I knew when I asked the question, like, it's not as simple as a logical proof. There is more.
No,
there's a lot more going on. But maybe Ed, David, James, if you have anything to add.
Well, one of the things is you just know when you have solved the problem, and it's something that comes with experience. You know that there are no loose ends. There's nothing not accounted for.
Okay.
When I look at something, people give me samples, and I think I drive them crazy because they ask what this peak is in the spectrum or in the chromatogram. And I say, that's fine. I'll glance at it. But then I start looking all around. I look to try to identify any small peak. I might try to identify a 1% impurity, a 3% impurity, while they want to know what the 90% is. And they said, no, I don't want to know that. And I said, well, no, it all has to make sense, because this might not be in the library, but one of these other components will tell me the type of chemistry that's occurring, what's the origin of this, what kind of material is it. So even if you don't know anything about the sample, it's packed with information if it's got impurities, and it tells you something about the context of the impurity you're trying to do. So if the library can find this peak, and they can find this other peak, then you might have a guess of the class of compounds, and then it's not a mystery anymore. The other thing is, a lot of times, if we finally get to something and the chemist just says, Jim, that doesn't make any sense. And I say, well, I think it does. And they said, I don't think it is. And I said, well, let's take it and put it in this 1 milliliter vial, and we can do a transamidation. We can do a transesterification. We can add a acetyl chloride to get what I want. And then it's what I want. And they say, oh, okay. We looked at it by NMR. We can see this grew to maybe a 5% impurity. I'll believe you now because you showed me that that's what it is. You believe so strongly, even though I disagreed with you on the chemistry. I do a lot of small reactions in 1 milliliter vials because you don't have to purify them. I have the LC, GC to purify them, so there's no need to purify. The NMR can look at mixtures. The things that what organic chemists hate is says, I want you to get me a sample and I want it to be 99.9% pure. And they say, oh gosh, take 5 minutes to make the mix, and it'll take 3 days to purify it. But I don't really need it purified to tell me that's what I'm looking for. So we do a lot of things like that. But looking around, just look around the chromatogram. That can be really valuable, just to find other things that you do know what they are, reflect on the stuff that you don't know what they are.
Very interesting. Okay. I guess I still have more questions if you guys aren't too tired of me. So the next question is about the use of high resolution mass spec and how that's helped with your ability to identify things. And actually, a correlated question is, yeah, I guess what technology, especially for some of our more experienced analysts, what technology has really changed and improved your ability to identify compounds with mass spec? I heard AMDIS obviously was very helpful in terms of being able to easily deconvolute things. Hybrid search. Yeah, I guess maybe just a little bit of background on how things have changed throughout your experience interpreting mass spectra, and then I guess the role of high res in your workflow.
I started out in 1978, I think, and I started doing accurate mass in 1980 on a VG magnetic mass spectrometer, and that thing was terrible. I mean, to tune it would take 2 hours, and about the time you got it tuned, it arced, and it jumped out of calibration. You had to do it again. I mean, so you'd spend half your time trying to get the instrument to tune, and now it's just so simple. Anyone can run an accurate mass instrument. You just put it in, and you get the results out the other end. And the other thing that makes it, Finn was talking about in one of their papers, they were talking about, accurate mass is not good enough. The isotope ratios are what make it. You have to cross those, and the isotope ratios with the new instruments are just wonderful, so that you can model them and take this molecular formula that might have been hard to get a molecular formula for something that weighs 300. You throw in the isotope ratios, and it becomes trivial. So I think that's what's really changed. The instruments are simpler to use, and the isotope ratios are good, and the sensitivity is phenomenal. And you could do accurate mass CI very easily, too. Well, that used to be a real pain on the magnetic instruments because you couldn't get anything to calibrate with. So all of those things have just made it so simple. So simple.
Can you hear me? Gary, do you have any comments?
Well, not really, because I don't do high resolution. I'm actually comparatively boring. I do GCMS, and that's pretty much it. And I'm looking at this primarily from the point of view of using it to build our library, and so we do the best we can with what we've got. But we certainly. One of the things you always look for is the question of did the material that you bought from somebody, did you get what you thought you got? Did it decompose? Did it decompose in the inlet system, which sometimes happens? And so those things are always something you look for. I don't know that that's changed any over time.
So not speaking about high res, is there any other either, I guess, instrumental or analytical advances that have really helped you, over
Let me say one more thing about high res before you go on, or that I didn't think of. If you're going to do spectralist database searches, you got to have accurate mass, period, to make it useful. So if you don't have that, it's not going to be useful.
Right, your search space is just too large.
Yes, can't do it.
Jim, what do you mean by spectralist databases?
ChemSpider has no spectra in it.
Oh, okay, I understand.
CAS Registry has some spectra in it, but it's not really a curator of spectra. But it's got a lot of information. It's got a lot of structures, and it's got a lot of molecular formulas. So I just call that spectralist. It's not really aimed at, you can't put your spectrum in and search it.
Well, one of the most powerful things for mass spectrometry for me is DART, because having that accurate mass and unambiguous elemental composition for the molecule is very important. And you can do that with DART with anything that you can get through a GC in seconds.
Awesome.
We do a lot of we do a lot of accurate mass in Fusion by LCMS. You run something by GC, and we're not set up for CI for one reason or another. I just take, if it's a major component, I take it over and infuse it by LCMS. Just skip the separation, and also do deuterium exchange there. I dissolve it up in acetonitrile with D2O, and I count the exchangeable protons, and that can sometimes differentiate an alcohol versus an ester. Those are all very easy things to do, and get accurate mass off of a time of flight LCMS by infusion is very easy to do.
Well, that's another thing you can do with DART is get deuterium exchange by blowing D2O into the open interface as you're taking the spectrum of the sample.
Awesome.
Yeah, I do a lot of evaluation. I do a lot of evaluation for NIST of EI spectra, and I wish we could use chemical ionization. It's just not feasible to do because of the numbers they do. But I really miss anything that we added to the Eastman library. We didn't know what it was. We did chemical ionization on it. It was just part of our routine daily life to do chemical ionization because the sources that we used were interchangeable without breaking vacuum. So it's very easy to switch back and forth.
You know, another thing is that you have to live with is the extreme differences in structures and the similarity of mass spectra. Arun, what we were talking about this morning before the session started was there is a spectrum in the NIST library. I can call it up and show it to you. And that spectrum has been in there for several years. It was measured by Chemical Concepts, said to be that. You feed that spectrum to that structured MS interpreter, and it comes out spot on. But it turns out that the spectrum for a compound that contains 2 atoms of silicon is identical except for the X+2 peak of one of the key fragment ions. And it's and you look at that, and it's far too high to be for the structure that is proposed in this.
And actually, for that example, David, those structures are so different that one would hope the retention index would tell you something about it, right?
Yes. Now, one of the things I didn't do was look at the estimated. There's no retention index for either one of them. And there's a good chance that the spectrum that is in this was actually measured with a direct insertion probe. That's another thing you have to keep in mind. You know, gas chromatography was not developed for 20 years after they started collecting and building mass spectral libraries.
Mm-hmm.
You have to be careful. The NIST library is just the quality is exceptional. It's just a fantastic resource, but there are errors in it. And I find errors every year, and I just trip over them. You know, all of a sudden you just look at it and say, that can't be right. And it's nothing that it was, there's pretty subtle stuff, but you have to be careful. Mass spec library searches are an aid to identification. They're not the final words. So be cautious, you know. If I give a user at Eastman the wrong structure, he's an organic chemist, and it doesn't make any chemical sense, then it gets to be embarrassing, and they won't believe me the next time. So I'm real careful about taking something at face value that comes out of the library. It has to make sense.
Mm-hmm.
Yeah, see, this is what happened with Billy Bob Bodecker, is that he took that hit list and said, this is the compound. And he made the fatal mistake of saying, the library says this is the compound, therefore this is the compound. Mm-hmm. And that's the time that you want to get a 32 caliber revolver and go into the toilet and do the honorable thing.
All right, but actually, with the with that example, that's actually a good point. I mean, we're preaching to the choir here, but I was asking about like the amount of time it took to make analyses, and I'm sure for all of you, you've gotten faster because you're more experienced. But I'm sure when you were starting, it did take a while to interpret spectra. Am I right? It's a skill. It's not just something that you know or you don't know. You get better at it. Is that right?
Yes, and one of the things is, in order to do this, you have to look at spectrum after spectrum after spectrum. And if you're starting out in this field, one of the things that I tell people that they should do is download the NIST demo from the NIST website and look at every spectrum in that demo and be able to figure out the fragmentation mechanisms for every monoisotopic ion. Check the isotope peak intensity ratios to see if they're correct. And just do this over and over. And when you've gone through that 3,000 spectra, go back and do it again. And then the other thing is that when you get your spectrum, even though you know that this is the compound, then evaluate it. We've made mistakes at NIST where we injected something into the GC, and we've said, well, this is the spectrum of it. But unfortunately, what we did was we had too long of a solvent delay, and the compound came out during the solvent delay period, and we had the spectrum of an impurity.
Aaron, I don't know any day that goes on that I don't learn something more about mass spectral interpretation. I mean, it's just a never-ending process. So it's not an easy thing to do. It's not an easy thing to do, but all the NIST tools make it much easier if you understand how to use them. But it's still a very difficult thing to do. And I probably told you, I don't know how long it took me to do the chemistry for that thing, because I often sleep on stuff. I look at it initially, and some days I'm smarter than others, so I'll sleep on it. And the next day I figure out something that comes to me. So it doesn't always happen just immediately, but maybe the duration was very long, but maybe the actual time wasn't so long. But sometimes when you look at something, it just doesn't make sense the first time. You have to sleep on it. Think about it.
Ed Earsman, I know that you haven't seen the technologies change as much as maybe our other speakers. But has there been anything over the course of your career that has really helped your ability to identify things?
Probably the single most helpful thing in the course of my career has been the hybrid search. That has been vast improvement, especially with a lot of these synthetic drugs where you get single point modifications, and then say a fluoro comes along, is like, oh wait, the identity search you don't get a great match factor, but hybrid search, you're in the 800s or 900s, and you say, oh, it's delta mass of 18, so I'm immediately thinking of a fluorine or other say a methoxy or something, like some other common modification there. So I think in my relatively short time, that is probably the single greatest improvement I've seen.
Well, in my long time, I would say that the hybrid search is the single greatest improvement that I've seen.
One of the biggest changes I've seen is chromatography. We used to take a stainless steel piece of tube and take it up on the second floor and tap it with a vibrator and fill it full of packed columns, and then we'd coil it around a tank and stick it up in the instrument and hope it worked okay. So capillary columns have been just phenomenal change in my life, and what you can get off there a lot more inert, so you can get things off that you couldn't get off before, and they're so simple to use. The first capillary columns were terrible because you had to sit down and blow an inert gas through them while you took a torch and straightened them out so you could stick them up in the instrument. So fused silica made a big difference too. So those things in computers. Oh God, we had PDP-8s that we had 2 of them that were terrible, that were next to the magnetic instrument, and the display on the monitor would go left to right as the magnet scanned. So I'm grateful every day for all the new technology.
Yeah, I agree with fused silica columns. That was a great change. And also, but on the other hand, fused silica columns started causing some problems because the chromatographic peaks can be too narrow to get a good spectrum of the compound.
I have a more practical question, possibly. One of the things James brought up in his talk was helium conservation. I know some labs are considering or have moved to hydrogen as the carrier gas. Are there any tips, tricks, do's, don'ts, things to be wary of if people are considering that process?
I have one word: don't. and you don't have to, because as James talked about on his website, he's got new devices like Thermo Fisher has a system now where they get 1 tank of helium last for 3 years. And that makes a huge difference. And Agilent has come up with a new injector. And a lot of these things can be put onto your old instruments. And with the cost of what helium is, it's easy to put those tools on. But one of the things is hydrogen is going to be tremendous problems, because hydrogen is you are going to have material that accumulates on the ion source that you're not going to be able to clean. But with hydrogen, it will clean it off and it can up your background. You're going to have problems with things like methylene chloride and hydrogen and producing HCl and ion source. Hydrogen can also react with your analyte in the ion source. And it's just something that can be, to me, too much of a potential problem. And now with these new techniques to reduce the amount, I don't see any reason to
Agilent's made a lot of progress in their current source, and it's much better. But the main problem is the signal to noise, because you can get a good signal. It doesn't do as much of the reductions. They look okay, but then you're always riding on top of this noise at every mass at the low end that affects your overall signal to noise. But they've made a lot of big changes. If you're just doing qualitative data at the high level and you didn't have a source of helium that you couldn't get at a reasonable price, I would use it for those use of applications for higher level qualitative type data. And I think ultimately, if you got better pumping and better material science, someone's going to make it work one day.
Well, it works because, remember, people doing GC in Europe used hydrogen exclusively for years. And when they did GCMS, when I was a product manager for the Varian ion trap, we used in Europe, we would use hydrogen as the carrier gas for our GC.
But they didn't care what came out the end of the column. As long as it arrived there is what they put in, they were fine. But when it happened in the source, they didn't really care if all of a sudden their aniline, nitrobenzene was part aniline. They didn't really care because they were just trying to detect it and quantitate it. So mass specs have a little bit more of a problem in that regard.
Yeah, that is the thing. There's a few cases where you get you get strange mass spectrometry if you've got hydrogen as a carrier gas, and there's just reactions going on, and sometimes you don't see them right away.
They sent me a file from Agilent. The guy had done one for their new source, and he was kind enough to send me one that had a lot of brominated, chlorinated nitro compounds in them, and it looked really good. They'd gotten rid of most of the chemistry, but he did admit when it was all said and done, I said, well, what about all these masses at every mass at the low end? He said, well, yeah, that's still, your signal to noise might not be as good as you'd like to on analyses that were pushing the detection limit. So, but they did do a lot better job on some of the chemical reactions that were occurring. I could take the whole library, run it in AMDIS, and process it all automatically, and I got all the right results with high hit qualities. So I think they're doing better. It's not perfect.
One of the interesting questions is if you take and do a library search of the NIST spectrum of oral hydrate versus the library, the number one or number two hit that comes up is going to be chloral, because oral hydrate loses water in the injector of the GC. Now, should that mass spectrum be there, and it's going to have the same retention time as chloral.
So in that example that you're speaking of, David, basically GC mass spec, you wouldn't be able to differentiate those two compounds because one, like when the analyzer sees them, this is the same compound that they see.
That's right.
Yeah, that's an interesting philosophical question about building a library.
If it was my library and I was at Eastman, I would put it in there and make a comment to warn the user that this is what happens when you do this. But I understand NIST can't really do that. We put a lot of things with no question marks, which with chemical ionization data. We put in something with a double question mark. We put in something with 2 question marks. We put in 3. Because a lot of times, if we just knew where it came from in an industrial process, the question marks drew attention to the user that they shouldn't get carried away on the structure, but it did tell them about where the sample history came from. So, but NIST they can't be doing things like that. They can't do that. I understand that. User libraries, you can take more liberty.
Yeah, so actually this was my follow-up question. That's a great point. So for most of our audience will be drug chemists or forensics related. Do you recommend building user libraries?
Absolutely. As a matter of fact, if you look at all the EPA methods, the EPA method says that you are supposed to search your compounds, even your knowns, against spectra that were obtained for known standards on that instrument. So if you have 10 instruments in the lab, according to the EPA method, you need to have 10 separate user libraries that you have to build for each one of those instruments. And I'm a strong supporter. If you're doing target compound analysis, you have a user library and you know what the compound is, and you have proof. Either you take the proof as that was what was in the bottle, that's what they said it was, or you do some other data. Now, a lot of forensic labs now are using IR and Raman, and I would have spectra of those.
Okay. So we
Aaron, we make our user libraries at Eastman. We use them a lot, and we might be I don't know, because it's hard to tell what other people do. We might be the only people in the world that use the NIST software to automatically combine 5 or 6 libraries from all our people that add spectra and update them nightly automatically. That just happens automatically. If they find an error the next day, when it rebuilds it again, it takes it out. That capability is within the NIST software, but I doubt if anyone else uses it besides Eastman. That no one's ever told me they did, but it's there and you can do it.
Okay, great.
I want to go back to the chloral hydrate question, because there's something. David said that the two would have the same retention index, and they have the same experimental retention index, but that's basically because the chloral hydrate has probably never been measured. The chloral hydrate should have a significantly different retention index, but in fact, you're probably always measuring the chloral. So it's entirely possible that no one's ever done a mass spectrum of chloral hydrate, and at least based on what I'm looking at in our database, no one has definitely done a retention index of it, because it's just impossible for the numbers that are there to be correct.
You're absolutely right, Gary.
So it's not that there's not a retention index difference. It's just that no one's ever measured one of those retention indices, and probably, I mean, for all I know, no one's ever measured the mass spectrum of it. I don't know. Has anyone ever done a direct injection of this thing?
I don't know.
Right.
It'd be interesting to do a cool on column injection where you lay it on the front of the column and then start the chromatography, but I've never done it.
Right. Right.
One of the things, but where would you check for something like that? Look to see if there's a very old chloral hydrate mass spectrum that was measured before the development of GC that's in the NIST.
Seems like your dogs are not satisfied with how long this workshop is going. We do have one more user or participant question. I think it's worth mentioning. So the question is about where do the MS or the mass spec for the NIST library come from? Are they all analyzed at NIST or a combination of in-house and submitted from industrial sources? Does anyone want to speak to that?
Well, I will. Historically, there've been a lot coming from the outside, and they're still evaluated, and we still do occasionally acquire things. The vast majority of the additions to the mass spec database over the last few years have been compounds that we've bought and analyzed at NIST, and that is taking a lot more resources than it, say, did 10 years ago. But there are certainly large collections that have come from the outside, and many of those are extremely high quality. And so it's not like we're objecting to data coming from the outside. It's just that right now, most of our data is coming from work that we do ourselves. And we have found problems with having other people do some of our work. I mean, it's harder to have the kind of quality control that we would like to have at NIST. It's not impossible, but it's harder.
Oh, Gary, we no longer, NIST no longer digitizes spectrum.
No longer, we haven't digitized spectrum in a long time.
Yeah, used to, spectra were taken from from literature articles and digitized. And NIST has stopped doing that. Now, that's an interesting thing to note, is that most of the new spectra that appear in the Wiley library are digitized from the literature. That's why so many of them are monoisotopic spectra.
All right. So
the other important thing on this, just one more thing, is it's only after NIST undertook this massive project of building the GC method RI database that we started really pushing to measure the retention index at the same time we measured the spectrum. Now, retention indexes have been around since the beginning of gas chromatography. And if you only had a gas chromatograph, that was the only way that you could do a qualitative analysis. So they're important, but now NIST has brought them to the forefront and made them more important. And getting contributors to make sure they give us retention index is difficult, because you do have to take the time, if you do it right, and run that retention index data file every day.
Awesome. All right,
The other thing, one more thing about structure searches within NIST are very good also, and I use them all the time to find model compounds. And especially if I'm doing a large molecule and trying to find out if it matches the spectrum, I draw part of the molecule because I'm trying to target on what it loses from the part that I'm interested in. So structure searches are very good. And now they have Inchy key, which is very good. If you limit the search by Inchy key, you find exact structures too. And I've got that all in my course on the internet, talking about using structures in the NIST search, if anyone's interested in it. But I use structural searches all the time. All the time.
So because we only have 10 minutes, I was going to do a round through and see if anyone had any last minute things to say. And you guys jumped the gun and said your last minute things. But I don't know, Ed Arisman, is there anything that you want to leave people with? Any key ideas?
Pretty much, I'll just reiterate the utility and value of doing retention indices, and how we can drastically improve our search using those. And I'll leave it at that.
All right, thank you. Gary, any final thoughts?
No, I don't think so. I wondered, I can't remember whether I talked to people about how they could find, when I was doing the demo, whether I showed them how to get and see and not see the uncertain peaks. But if anybody is curious about that, they could write me. Otherwise, I can take 2 minutes and show it. But I don't think it's worth it. So we'll go on.
All right. James, any last?
My last thoughts go to what Gary just said. Everything that Gary's told me, he's told me so much good stuff about AMDAS. I put in my AMDAS course on my internet thing. So if I had to say something, you've got all these powerful tools, but if you don't know how to set them up, spend the time to learn how to use them properly. And I tried to share that with people in the course and take things that David have told me, Steve Stein have told me, you've told me, all of you guys. I try to incorporate them in the courses, because if you don't know how to use the tool properly, it's not of very much use to you.
David, you want to close us out?
Start your data acquisition at M/Z 10. Don't throw away data, A, and B, don't waste your money by having leaks that destroy the stationary phase of your column.
Awesome. All right, Ed Cisco, do you want to close us out? Actually, I forgot that you're our moderator.
All good. I don't really have anything else to say. Thank you all for presenting. I personally have learned a lot over today's course, not being an expert by any means myself. We'll get this posted online so everybody else can see it. And if you have questions, if you have anybody's email, feel free to reach out to them. If you don't have their emails, reach out to Arun or I, and we'll get you in touch with whoever it is you want to be in touch with. So thank you, everybody, and have a great day.
Thank you, guys.
Thank you.